Putnam. The real goal is to move on to CDCL. It's a little trickier because the construction we've done is definitely too many copies of formulas and stuff. There might be a better representation, but again, we have to think about that. The data structures I'm using aren't bad. Using sets and stuff already solves some of the constraints, even, or the rules that are applied, like the multiple rule. Now you don't have to worry about multiples or checking for that because we're using sets. So basically what's going on here is that this isn't working, and so I've put a little print statement here. That's all I did was mostly just do research looking into CDCL, but I want to finish this one off because it's kind of constructive to just do it. We have to fix this. I mean, a lot of these things where we're calling solved vars and all this, it's going to have to be extended. But actually, the truth is we're going to get the most wisdom by doing CDCL. After we do CDCL, coming back and fixing these to be more efficient or more optimal is not too difficult. So basically what I'm seeing here, just by, and as I said, all I've done is I moved this into X and changed it here for the case splitting so we can see what it's splitting on, and we print the clauses. And basically what I see here is I see that everything looks good, except here it's going to use this pure literal rule. And again, since we're only trying to make an oracle that says sat or unsat. And in terms of actually figuring out anything about that, we're going to still store solved variables that have to be true. But those will be contaminated if we use this pure literal rule. So we do have to remember the problem with the pure literal rule and the case splitting rule is, well, the case splitting rule doesn't contaminate these solved variables, but the pure literal rule definitely does. So one idea is just to get rid of that rule. But that rule's not working, and we might want to think about why it's not working, because clearly this equation has three solutions. Obviously, it's seeing 6, -8, 5, 3, and 6 and 3 are not really solutions because you see 6, 3, -3, -6. So obviously, it's getting the 6 and 3 because they have become, they're maybe pure literals, so, or something like that. So actually it's a question why that's happening, but it seems to be that that's the case. So this pure literal rule's definitely messing things up. Put another print statement in there, and we should be able to easily see just what's going on. Okay, so we see actually the pure literal rule didn't seem to mess anything up. But the unit prop is wrong because, I mean, we add a literal 5 because -5 is never occurs, so 5 is pure, so we add 5, which should actually make this simplified down to nothing. I mean, obviously the 3, -3 should give an empty clause. That is a conflict. That's exactly what a conflict is. Two unit clauses that are in conflict with each other. That's always a unsat. But this shouldn't be unsat. Logically, we can see that this is not unsat. 5 is true, and you're done. I mean, then everything deletes. So the question is, how come we got this working in a pretty broad sense, and yet it's obviously not working? I see it removing all the clauses, so there's absolutely no good explanation that I see here for this. It's weird. Something is going on here. So we look at the map, and -5 is an empty set, and 5 contains all of these. 3, -3. I'm almost at a loss here. This is so weird. Okay, that's a bit ambitious. Comment some stuff out here and see what is going on. Huh. 5, and it finds the 5 clause. This is like, it just defies all logic. I mean, okay. Obviously, it should be deleting all the clauses. I mean, I see it's printing the map and the clauses here, and I see printing. Oh gosh, printing clauses in map, and prints clause. It's just defying logic here. Oh. Okay. Whew. Okay. Micromanagement. I'm of course worried about these little micromanagement details. But what can happen at any time is that this can happen. Now, I don't know what's causing it to be resurrected. Yeah, this is causing it. Yeah. I don't even know the best place to look for this, but basically, if the length of map sub y is 0, and the length of map sub minus y is also 0, then we should just actually delete map sub y, delete map sub minus y. I think this is the only time this can actually occur. Okay, so that should have fixed it, maybe. No. Oh, wait, actually. Okay, so one thing we may want to do here is start. We want to turn this into an oracle. As I said, this DP algorithm, because of the way it works with sat or unsat, it really is just an oracle. So I mean that the logic is not defied, of course. It's just some little thing. Now, like one question is, does it still work? And it's something to consider here. So sat, empty, set. I mean, these are useless things. And unsat. Whoa. But it, yeah, because it's doing that enumeration. It's just not being careful here. -231 is the solution. I kind of feel it actually works, but first off, the pure literal solutions could just come first. Because of the way we're doing the enumerator for this, we can actually use that rule because we can just block those pure literal solutions later and they won't be pure literals anymore. And again, though, this is going to be highly inefficient, but nonetheless, it at least would prove that the algorithm works. So this is already returning an effective Boolean by saying either solvars or none, so that's okay. I'm okay with that. However, here is the problem. It is not returning complete solutions. So I'm just thinking about the best way to do this. I think we could get all the variables using some trick, basically. Just make a big set, right? So just take all the clauses and union them together. I think this will work. So you just say like all vars equals the set union of clauses. Just, that seems too easy. Yeah. I guess we have to use the star there. No, it doesn't apply to a tuple. I don't particularly like this, but so I guess that works though. So again, we can see that all of them are here. So there we go. So even if we've done better here by using the absolute value. So we're just getting all of the variables. So basically when we have a solution that doesn't have that length, we know that, you know, something's missing from it. We can do a simple set subtraction, which is actually efficient because we already have a set that we're subtracting from. So of course it has to make a copy, but it's fine. One moment, I need coffee. Coffee is coming. And I think we're going to be able to polish this one off. It won't be efficient, but it will work. One thing that may have happened is I may have broken the solver. Unfortunately, I don't really know without running it again. Yeah. The problem is I use those empty map entries to determine the free variables. So again, it's like everything's a trade-off here. So my opinion is we just take that back out. It was just kind of like experimenting for now, because now it works again. So it works again, but this one won't. But we also know how to deal with that. We can just deal with it in pure literal as well. That was the other option. So there we go. Okay, so that is the same now. So when it returns this kind of like partial solution here, we're going to need to like gently guide it along to maybe find more of the solution. This is going to be a little bit tricky because, well, yeah, we may need a stack or something because we're going to kind of have to keep track of stuff here. And obviously we don't ban a solution yet until we have a complete solution. So while we don't have a complete solution, we can't even change the clauses. We can't even start to find the next partial solution. Actually, we can ban a clause as soon as we find any solution. But the problem is where to. Okay, well, one thing we're going to do is we're going to take the length of the solution. We know we want that. Otherwise, we can yield it. So what we can do is we can randomly set one. This is actually trickier than it seems, because I want to make it reasonably efficient. I mean, I see that we have an oracle here, but I need to, and it's a terribly inefficient oracle, but nonetheless, it is an oracle that tells us sat or unsat. So the question is, how are we going to use that oracle to like start breaking an equation out of all this? Well, we're going to obviously one by one start trying more combinations and see if that gives us a bigger solution. The first thing is everything we know of the solution, those are now unit clauses. So we can actually like immediately just say, oh, no. Yeah, we can go through the solution and we can add this list to clauses. So if we do that, though, it'll just return an empty list the next time through. So we need to do that. Yeah, like unlike this, where we just added one big clause. I guess we could make a list too, but it doesn't matter. What we want to do, though, is we want to add like a bunch of unit clauses to say, hey, we know those were already solved variables. Even if they came from a pure literal. We'll take out the pure literal solutions, so it doesn't matter, and we'll get the non-pure literal ones, because pure literal ones, they are solutions. They may be getting rid of solutions, but it doesn't matter because we're going to iterate through. So now we have something, but we need a little bit more than that something. And so the thing we could do is we could say all vars Now we can't subtract solution, but what we could do is we could say we could subtract the absolute value because we're just looking at the positive ones here. And then we could, like take next iter and we can get like some variable. Now, we're not there yet. We're definitely not there yet. Thinking about this, we also need to add like this other unit clause in. However, we're also going to need to add in the negative x version because we don't know if that's going to work or not. So now, if this actually makes progress, it doesn't mean we can avoid this. We still need to do this one. Because if this makes progress, it may only make more partial progress, and it may still hit a dead end. So because of that, we actually have to remember that, we can't just keep going without this one somehow around. So we're going to need to well, if this returns none, then of course we don't need to remember it. Then we're done. Then actually this is all we need. But if this doesn't return none, and this doesn't return none, now we have like two partial solutions we have to keep branching on. So probably you can see where I'm going with this. We're going to probably need a stack here. Again, we can always ban a solution here because it just doesn't affect anything. I mean, it doesn't change. Oh, well, actually, no, it would change these. Hmm. This is trickier than I think. So I mean, we take a random variable, we apply it, and we can ignore the none ones. I kind of feel like making just a stack for this is probably the easiest thing. We can push all the solutions onto a stack, and then if we can just do this and just add more solutions to the stack. And if it's none, we just don't need it. We can get rid of it. It's the unsat case. And then, yeah, I'm just kind of wondering if this is going to be a problem, but I guess it's okay. Whoa, whoa, whoa. Wait a second here. Wow. Look at this. It found two solutions to this formula. Wow. It solved this one. Yeah, it solved this one. It solved this one. It's starting to work. It's a bit confusing here though, because I have too much printing still, but okay, we can start deleting all the printing here. I hope we can just start deleting all the extra debug printing. Okay, this would be cool if we have DP working. Okay, so what do we see here? Well, we see we want these sorted. I mean, the usual stuff. I'm just going to copy paste that one over here. So we can just, when we're going to yield a solution, we can just yield it in a nicer way. Okay, so what do we have? Now the order might be different, but we have 4 solutions. Equivalents, we have these solution, we have this solution. So the first problem that I can see with what I'm doing is -1, -3, -8. So we get that, and we get the all positive -7, -8. Yeah, we get this solution, but we don't get the one with -6. So this actually almost, as simple as that, almost works. Oh, but we don't actually, yeah, when we ban a solution, we probably need to start fresh. We don't need to worry about branching anymore because it's at like the end of the chain. As far as I can see, this is all I have to do. Yeah, heck, we can just do it like this here, if we want. Wait a second. Okay, it found all the solutions. I mean, it's basically starting to work, but the problem is it found a solution twice. What I'm going to say, though, is this is on the verge of working. It's on the verge. There's some little issue with the logic here. I mean, I basically know what's going on here. Basically, when we're adding this here, like the way we do this search here, we could have already added 2 solutions to the stack before we had a chance to like process it. Because I'm sure what we could just say is if it's, I don't really like that, but you know, we could do something like that. That you know, if sol in stack, you know, if there's a second copy of it, I think that would work. No, it didn't. Okay, never mind about that. I mean, I guess it is right though. It finds this solution first, and it's just like sitting on the stack. So by the time it's like banning the solution, it's finding it again. See, the reason I don't like removing it from the stack is it really suggests there's a complexity problem here. It really suggests that what we should be doing is not this kind of methodology, but we should do something that like straight up takes care of it before this can happen. We don't, because we don't want to find duplicate solutions. It's a terrible thing to be doing. My opinion basically is that, yeah, if it's none or if it's equal to the length, then actually we want to do this as soon as possible before, even before calling this again. Although actually it doesn't matter here. But we want to do it before, you know, old stuff on the stack starts processing. Um, I know I'm thinking about this because we had, like with two set, we had a way to deal with this. I came up with a good method that was pretty concise. What do we do here? Yeah, that's right. Oh, that's right. The problem is this is different because we don't have like pure literal nonsense going on, which is like causing some, because we do have to like restart at that point, and it's very hard to keep track of, you know, this kind of. Hmm. I mean, I would say we do the same thing we do with 2SAT, but when you have like this, when you have this situation where you have these pure literals and you have to restart, again, we want to do like this idea that you're going to only go through every solution only one time. Okay, I know this is horribly inefficient. It's a joke in terms of like, well, actually we can't use this one because, oops. I just want to see if it can actually find a single solution. It's slow, but it's finding them. That's how I would describe it. So DP is working in a certain regard, and we are using that splitting rule. It does seem to be giving us SAT or unsat correctly now. We're much further than we used to be, but my construction for how to use that oracle to enumerate solutions, when the oracle is applying some like pure literal rule, which preserves SAT unsat, but does not preserve the solutions. So now it's actually reduced the solution number of solutions of the equation, because by assuming the positive that or something is true, it's excluded all the false cases just because they're unnecessary to determine if it's SAT or unsat. But we're writing enumerator. Enumerator is more general and more difficult. I need even more coffee. This is a coffee job right here. Okay, more coffee. Maybe CDCL. I want to give up on this getting the construction right. I'm wondering if it's going to be quite difficult. See, the problem here is that I don't know if there is a simple solution. I can start trying to code out solutions, but I'm just, sometimes you have that feeling that you're maybe trying to do something, maybe the literals shouldn't be the way they are. So, I mean, at this point, it's hard for me to say that this isn't maybe the wrong approach. But, I don't know, but I don't want to see partial solutions on the stack again. And the problem is adding this blocking clause, I feel like, and starting over might be a real problem. One idea is just to print the stack. Oh. Okay. So looking at the stack is very, very helpful here, because we can start kind of thinking about what's going on. Obviously, we never need to add nuns in. We could filter those first, but it doesn't matter that much. Those are not the important part of any of this. That's a slight optimization. Okay, so 6 minus 8, 5. Now it's applying one literal, which solves the whole equation. Six minus 8, 5. 6 minus 8, 5. What's different here? Maybe it's 7. I think it's applying 7 and minus 7. It could be 3 and negative 3, but yeah, so it gets two solutions. And then when it bans the solution, you see it gets 5, 6. And this is not good. Here it gets 5 minus 6. And this is good. So when it gets 5, 6, it's banned one of these two solutions, but obviously it didn't ban both yet. Yeah, I guess. Okay, I mean, actually, this looks. I'm still suspicious. I'm still really, really suspicious. But this looks like it's solvable by just, doing an inspection here. So we do want to save this. Might as well just be consistent here and just save it everywhere. Just a tiny little optimization. But what we need actually is to ban the solution here. We're not going to ban it here. So before we continue our search, we want to ban any solutions so that, I think this works, actually. I think this works. I just want to think about the case that this could still hit, because the first, it just finds a unique solution right off the bat, or a full solution. Although I don't think that's very... If it finds a full solution, it means it's the only one, really, doesn't it? Because, I mean, this is going to be none. I think always. Because the way the DP algorithm works. So if it gives back a full solution, it means that it can't give back a full solution if there's more solutions. That's kind of the key. You have to, like, force things to give it a full solution. So it will only give back the only solution. So we really don't need to worry about this case. What we do need to worry about is these cases right here. And so we would need like an extra, check here. Feels like I'm repeating my code, but I don't know a better thing to do before we put it on the stack. In fact, we don't even need to put it on the stack. I don't guarantee this works though. Actually, honestly, this seems terrible because I'm like going to be duplicating all this code all over the place. I don't like it, but just for the sake of seeing if it works. Oh. Okay, so we need another variable here, and that's the problem. I really don't like this somehow, but it might work. We can't corrupt the solution variable because we. Oh, that would have been. Oh, before we were directly pushing the solution. So let's make sure we don't change sol ever. Here we could change it, but you know, just to be neat about this, I'm gonna say let's not do that. Don't like it because I'm repeating all the code, but as long as we're not using this solution except for here and here. Well, maybe here, here, and here, yeah. We use a different variable, then this might work. Okay, it does work. And actually, if you look at the stack, that's pretty good. Because, again, we see all 5, 6. It's okay because it's banned the solution that it found before. You know, the first 5, 6 solution, and maybe even the second. It's banned those solutions. So by just inverting them like this. So actually, it works. Okay, I mean, as far as I can tell, this is a clean, it's not efficient, but it's a working enumeration algorithm now. Is it absurdly slow? Well, probably. Is it going to be case splitting forever here? Maybe. Let's just see how, there's only a few solutions. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. 8 solutions. Yeah. 8 solutions, and it's, you know, it's not even finding a single one because of all that case splitting going on in there. Could print the stack. I mean, we can see if it's even returning from here, or you know how this is. I really somehow I don't like this, but the problem is before something goes on the stack, certain processing is needed, except for this one case where it finds a unique solution from the get-go. I mean, I suppose the other option is to restructure this. Yeah, actually, this probably should be restructured. So we push on the stack, the next one to try, and every time it just calls DP, and that's it. And if it finds a solution, it yields it, bans it, and this way, I still feel it's gonna find a bunch of unsat cases then, but where you know it's basically banned enough solutions that there's no more left for certain paths. Yeah, that is some tricky business right here. So yeah, I mean this is just too inefficient to be worth talking about probably. No solved variables. Here now it's up to 20,000 clauses. I just want this to work to have some confidence in the algorithm. Uh, if there's anything I can do that would like. Hmm. Yeah, there might be some like optimizations here. I don't know if it's doing some, not so smart splittings here. Like, are there certain variables that it could just be optimizing in some way, like. But again, I kind of feel like if the map was empty, if it was a free variable, I don't think it would be affected at all because a free variable uh, doesn't really have any meaning in here in the splitting because it's going to go through map var, which would be empty. So zero and zero entries is obviously not a particularly meaningful variable. And if it's a pure literal, it should be handled here because that would actually be relevant here. Obviously, it would be one of these would be zero, so it would do nothing besides deleting the variable, which in a way is okay, but it should have recorded it as pure first, which I think it does, so it's okay. Yeah, it should be okay. So there's kind of this question: are there any tricks that we can do here? I mean, we can of course we can do like silly things like this. Say like, okay, maybe one set construction is more efficient, and the or can just happen kind of automatically. Do something like that. Probably that's a little bit faster. Oh no, it doesn't work at all. True. Probably that's a little bit faster. I'm not even totally convinced of that. Uh, but I guess the problem is it's just like if we look at the length here, it's just probably an explosion. I don't see that, with such an exponential growth, I don't see, and even if this worked, it would just still be so slow for the rest of it. There's really no hope here that I can see. Yeah, I need like smaller examples. These 20 variable ones are already too nasty for this because really it has to do with the clauses and stuff. So I mean, this this splitting algorithm is just it's creating way too many clauses. Now, there probably are some tricks to cut down on the clauses. Like, we could do some subset and superset queries, and that's probably like my instinct is that's the next one we could do. So we do tautology, we do pure, we do split, we do unit. Uh, we don't do substitution though. So that is one. Multiples we do. So that one's like part of the construction. So you can almost just put a comment that, so there we go. Multiple literals. We don't need any special sat, unsat. Well, we have those constructions because those are the any zero length clause is unsat, and zero clauses is sat. So we have that construction, but we are missing one construction. And I'm going to say it's worth investigating this because the, the, the problem I'm getting is it just sounds like kind of a, I mean, it sounds nasty to do this one. The problem with this is it's going to be n squared, but I mean, it's better than an exponential growth, I suppose. So sorry, substitution subset. So what we do here is we just, now one way we could do it is we could do it when we're adding them here. There's two possibilities. So the problem is we have to go through every clause with respect to every other clause, and check subset. Or I mean, we could do every clause with respect to every other clause, but not vice versa, and just do superset and subset. We could try to do some combined operation. I almost feel like it is more smartly placed over here. And this is why people use the tree data structure. So the tree data structure would allow you to maybe more efficiently do all these subset, superset queries. So this is, now, will this be a subset of something? Which ones do we delete? The superset can be deleted. So the subset's the one you keep. The superset's deleted. So we don't want to add it. If, again, this is kind of ridiculous, but you know, if any C for C in clauses, and wait, I think we want to say clause dot is superset of C. So if it's a superset of any clause, or we could say it's not a superset of all the clauses. For all clauses, it's not a superset. Then we can add it, and maybe that's enough. Oh. Clauses. Ooh, that's dramatic. That's dramatic. Okay, that actually, oh, that is really dramatic. Look at that. It could work. Wow. Well, that, I mean, as I said, maybe that's some kind of n squared-ish type of algorithm here, but oh, that's so cool. So it's, whoa, okay, I don't know what's going on here. I see like lists, oh, because I'm printing, where am I printing now? I don't remember. I must have some weird, oh yeah, here. Okay, so we don't need this anymore. So the key is we want to put a comment here to say this is another operation, you know, subset rule, any superset clause. Now, the one thing we don't do is we could do this. This is another one of those rules that you could do when you're building your initial clause list, because this could actually occur, you know, these bigger clauses should never be a subset. Because again, you're making actually, I don't want to guarantee anything here. We could check that type of thing. So we have that, but that actually kind of amazing. So this, it just shows, it goes to show like why, oh yeah, okay. Well, the question really becomes like, how long is this going to take, and will we get correct solutions here? Because if we do, that's kind of impressive. Okay, 2 minus 6 minus 8. Is that even like in the right direction here? I'm not sure. Doesn't look so good. I have no idea. Whoa. Whoa. Hello. Whoa, it works. Oh, that's awesome. Okay, okay. So I mean, I'm not saying this is anything wonderful, but honestly, we have DP working. That's DPLL off the bat. Literally, even with, instances that are, almost considered too big for DPLL, by being smart in this splitting, we got it working. So that's two of the three promised algorithms. DP, which is ultimately an oracle because of the way it uses two rules. So the other thing we should mark is preserves sat or unsat, but does not preserve solutions, unique solutions, I suppose. And the same thing we can say on this. Okay, this obviously doesn't preserve unique solutions because it's applying literals. But the case splitting, we can put a different comment. But does not give information about variable used for splitting. So again, there's two problems here. This one actually will find a solution. It's aggressive, kind of. It's an aggressive strategy, and it's good for starting. It's a good starting place for finding the easy solutions to start before you ban those solutions. And this one, it doesn't actually. It actually removes information. So. So effectively, also it messes up the kind of unique solutions, but in a way not, because it doesn't actually say that this variable is true or false. So it just doesn't say anything. It just basically gives a free variable back that's not really free. It has to be more or less deduced. So that's why I want to kind of say something different. But both of these are special. Leaves it as a free variable. That's basically what you want to say. And now, actually, this is great. Honestly, this is better than I thought it would be. I don't want to print these anymore, and I want to stop this nonsense too. So if we're gonna do this, let's just do it right. So let's just say DPLL equals that, DPL equals that. PyStat, we'll rename so we don't use the function name. And then we can actually assert, without recomputing, because this is just too stupid to do that, assert psat equals dpll and dpll equals dpall or something like this. And then we just want to like print something to know that, something's actually, how many solutions this dp works for now. Okay, so yeah. Again, we should stop printing and we should start saving first and this kind of stuff. But if this works and it does enumerate all the solutions for a large instant, that's pretty impressive, because it does say that, just using some good logic here is enough to do the job. And yeah, it does look like it's getting something here. I mean, oh yeah, well, if it doesn't work, that'd be annoying. But if it does, there's no way this equality is going to hold. So I was going to say we can actually almost delete the stack stuff. Oh, pass. Set object is not callable. But that's really good. It's humoring me. I mean, this is just funny how that actually works. It's slow, but you know what I mean? Waiting a minute to see something like this work is... Oh, yeah, yeah, okay, so don't... Just use smarter variable names or something. We should probably just save them in a list and, you know, say all need to be equal. So actually, here we go. Using an oracle, we now can construct sat instances. And this is an oracle which gives back a little bit of information, but it's tainted by pure literals and case splitting. So it has like free variables that aren't free in the solution. It gives you some solved variables that'll have real solutions, but it also gives you these pure literals, and then it gives you one. It doesn't give you ones that are, you know, basically ones that it had to split on. So they're free variables, but they might not be free. So only one route might work, and you don't know which one to, you know. You don't know really anything about that. So it's kind of, well, it is what it is. Okay, so I think we're good. I think the point is we can move to CDCL. This isn't bad. This is like exactly what you want. Is you want you want your basics down pat and reasonably efficient. This is not a spectacular sat solver by any means in terms of like the top sat solvers of the time. They're doing a lot of fancy tricks, but this is now like, you know, algorithmically, it's nothing to laugh at anymore. It's for being a little toy. This is now a actually good for a toy. It's what I would say. It's an excellent code for a toy. But if we wanted to be cutting edge performance, we'd have to do a ton of like, you know, details on, especially where we get the next variable, especially where we're doing these any and alls. We want to have like maybe a kind of like a table of, you know, how many literals mapping to clauses, and you know, how many times a variable appears in different clauses and these types of things, so we can do a bunch of heuristics. Basically, it would just be a mass of heuristics. But what I've done is I've done an elegant enough construction that uses decent, reasonable data structures. And yeah, I mean, you can see there's nothing in here that's shameful anymore. We're using sets, we're using, you know, dictionaries and stuff, but we're doing everything so that, you know, there is some inefficiency for sure. Like even in the unit clauses, I could optimize that, and probably I should. But you know, I mean, you have to just think. And the subset, superset, yes, using a tree data structure would be far more efficient to do that. Okay, sure. There's special data structures to do exactly that, because the tree could store like all the subsets and sets kind of together in a hierarchy, so that it's the queries for subset and superset are lightning fast. And in fact, it could check the whole subset and superset without going through everything. It could just go through the tree and find. But again, this is like, you know, I've done a project with a data structure like that. I even have it. It's in Python. Reasonably good, reasonably efficient. I implemented it even in C to be more efficient, or I think it was Python. Yeah, I used. Don't remember. There was another technology involved too. No, it was Python. Yeah, I did it in Python. So that's pretty good too. I think it's called Python. I don't know where you do the C Python. C Python maybe is a better way of saying it. So, but I see it written as like Python. So of course it sounds more like an S than a C. But again, Python is because there's no other way to say it. That's like Python, you can't use the K sound for the C in that case. It has to be Python or C Python. Anyways, this is going forever, isn't it? Yeah, but it's not crashing, and I imagine it does work. Now, the one thing I've mentioned is that the subset case might be something to handle. Because if we do find a subset, it should be eliminated. But then we actually have to delete something, and we have to delete it from the map, and this, that, and the other. I would say we should write that function or move to CDCL. That's probably the okay. So it passed. Okay, we can see it's slow, but it works. So again, the easy thing to do here, if we want to like kind of again, we know this could happen initially, but I'm assuming it doesn't happen initially. So this actually would be another simplification we could. I mean, immediately finds it. Um, so the first idea is to write the subset case. So we can actually write like a special remove subsets. And the way this has to work, as I said, it's like n squared. It's not. But again, solving this is just annoying. So I'm not particularly racing to solve this. Now, of course, we do not want equal clauses, but we do want equal clauses, but not equal clauses that's actually the same reference. And so this might be an annoyance as well. That has to be solved. All right, I went to the toilet. I really had to go. Drinking too much coffee, and that's what happens. Okay, well, whatever. So remove subsets. Okay, so we go through the clauses. Now, clauses is a set, right? So I think we can just use is. This is total n squared. So since we're doing it n squared, we won't do subset and superset. We'll just make one query or another. So, we can then just, or actually, yeah, we still have to deal with the reference issue. It doesn't, I mean, we don't have to, we can do this a little more simply by doing the same logic as here. Let's call this one clause. So if any clause is superset for now, this actually would be excellent in DPLL as well. I mean, obviously, this reduces the number of clauses, and it could certainly, and these clauses are absolutely useless because the extra terms that they have, or they're the same clause, they don't actually tell you any information. They don't make it any. They're useless, absolutely useless. You might think that extra ors in there, but extra ors do nothing for you because there's one that already says one of the other ones has to be true. So these extra ones will never matter if they're true or not. In fact, it will cause pure literals and other things to maybe. Well, I mean, yeah, it could affect some of those things, but it doesn't matter because they're totally spurious. We'd rather have a free variable than a pure literal in those types of cases. Uh, Again, free variables are not harmful in the case splitting case. That actually turns out to be really useful. A free variable, you just delete it, basically. It's just a clean deletion. And we just made sure here to be careful with those free variables, not to pretend they're pure. And in the unit case, we don't delete them because we did some stuff with DPLL. I mean, these are all like the details you get into, but again, I've tried to be really generic here. I've tried to make this code as friendly as humanly possible. Like trying to be efficient and friendly and generic and enumerating solutions, not just doing sat on sat, showing how we can adapt an oracle. So that I think this is really kind of instructive that we can take an oracle and we can do something. Actually, it's efficient enough that it can do some large instances in, it's slow, but it's not the end of the world slow. It's reasonably good. So that's like where we're at right now. And I'm going to keep drinking coffee like a madman. Coffee is code. All right, so back to action here. As I said, I don't like the duplicated code in here, but I'm more concerned about being accurate and efficient uh, when I wrote it, and I haven't. There are several places to clean up here. I'm not perfectly happy with all of this, but again, it's going to turn into this kind of beautifully simple generic construction where you could customize this code. First off, it shows perfectly the details of the algorithms with some kind of reasonably smart data structures, sets and stuff, and how you can do things in Python. And the code really this does not look like rocket science. Again, we're doing some copying of clauses and stuff. There's always questions about aren't there other ways and there definitely are just so many other ways of doing this. Again, there's so many trade-offs here. So I've just chosen one route, and I'm not saying this is the best. This is gonna fail probably when we go to CDCL, because CDCL is gonna need more info about like what unit propagations have been applied. It needs a history. It needs some kind of memory. So that's the case. No matter what we do here, I need to get my coffee. And so basically, what I'm seeing here is that uh, we do want to like deal with some of the last key aspects of DPLL. So all of these things like pure literals, these are all core ideas. And even though we don't always need them, there's like so many ways you can use different ones of these to accomplish the same thing. We want to kind of have all of them implemented. And this is like the last one. So if it's a superset of any of them, now we want to delete the clause. So it'd be kind of like clauses. Oh, we can't do that, can we? Okay, I mean, I don't know. Either we can make a copy of them. I don't want to do that. We can just add it to this list. Now we're not enumerating it, so we can delete from it. But we need to clean up the map. And it should be very similar to what we do here. N squared. I don't deny that. You know what this is going to do? It's going to start cleaning up the unit literals, isn't it? Yeah. It does the same thing. Because if it finds a unit literal, then, well, anything that's a superset of a unit literal is just going to delete itself, because obviously it does nothing to the formula anymore. Oh, what the heck am I doing here? Yeah. Don't forget the self-reference case. I just want to see if it's actually doing anything. Oh. It's doing quite a bit. But it works still. The question is, can we get a subset here? So we could add subsets here. So this is very interesting because it means that well, it's annoying at the same time because we're already doing something inefficient, and it's like, well, do we want? We don't. Of course, we don't want to add them, but then it's like, what about these subsets? Oh, you know what? I guess it's happening. Oh, we should do it before we add it as well. 3 negative 2. Yeah, so okay, so definitely it can add a subset, which means it should be deleting some of these other ones. And honestly, I think it'll improve the speed as much as this is still an n squared. And it's kind of starting to be kind of stupid that we're doing this here, but then we want to do it again. But at the same time, it's not, because probably it'll end up just being a lot faster if, you know, maybe even we do it after tautologies. The question is, did we get a huge speed increase or not? Or is this n squared going to be actually, oh, well, pass. I mean, that wasn't too bad. Probably we should be using time it by now to measure some performance here. So this isn't bad though, because again, we have a construction here for enumerating solutions. Again, as I said, I'm not happy with the duplicated code here. Definitely, the problem is we have to be very careful with this because honestly, much faster, much faster. It's working, and this is not bad. It's at least the code is correct now. That's all I'm going to say about it. We've gotten correctness. Now, does this need to be refactored? Almost for sure. Is it a little bit trickier than you might think? Probably, because we need to be careful about well, these don't affect each other, so I mean, technically I could already shorten the code a little bit, as far as I can see, because this is, these are, the bands of the solutions aren't going to affect each other here. I mean, obviously, totally different because they already have a different forced literal. I mean, basically, I guess my idea is that we could just do something for sol n in this comma this. That is one ugly long line. Maybe I can actually make that a little better too. But then we can just, theoretically, that should be okay. I mean, that at least starts to, I mean, this is just the type of stuff you think about. At least it starts to tighten up the code. It's not bad. Honestly, this isn't bad, because now we've just got one more duplicated case of code here. I almost have this feeling that we could hack this somehow to, you know what I mean? So sol n is enumerating this instead. Actually, that's probably what I would do, to just make this as simple as possible. Again, I'm not like saying this is impressive performance right now, but it's, DP is not even considered to be a practical algorithm anymore. This is just more like something we're doing to make a decision on if we can do things reasonably efficient here. So I think it's okay. I think it's okay. So I'm going to put some of these, I should do this. It's not really nice to use stuff and not remember what you were using. So I use this to deal with all these different things. What else have I used? Okay, for CDCL, I was looking through several things as well. Now, have we even started CDCL? Yeah, I've got other places I've looked, but again, not all of them were particularly useful, so... This one's from Berkeley. A lot of academic classes and other stuff have used this type of stuff. Yeah, I probably used some more things. Okay. Again, I'm just recording like I'm just trying to record what we've done here. And I think, yeah, this one, I think, yeah, it has more information about stuff. Yeah, this one, I think, okay. What does this have, DLL? This really, Yeah, okay. I mean, the one, this other one. Well, we're gonna put it in the list here. Again, when you use a bunch, you do a bunch of research like this. It is good to kind of remember what was useful in that. This one is good for the CDCL, so maybe I should move that comment somewhere else. This one I used as well. So you can see I did a lot of research, and I'm just recording what I looked at. Not just Wikipedia, even if I did use Wikipedia. Okay, so let's see. Where is my construction for CDCL? Oh, we don't even have one yet. Okay. I think it's constraint driven. Oh, DPLL. Do I not put the Wikipedia link anywhere? No, I don't. Are there any other variants here we should talk about? I mean, mostly unit propagation. This is just a separate comment, nothing to do with unit prop. Pure literal, case splitting, tautologies. Could put some comments about these. The subset rule. This again, there are definitely a million different efficiency optimizations, and that is what modern stat solvers generally do. Before you get into heuristics, you need to have good code. You need to solve the basis of the problem first. This is a great rule. We could even use this, and we could even use tautologies maybe in the DPLL algorithm, which should be a lot faster if we do that. Again, tautologies always can be removed. It wouldn't harm anything, but since we've got some finicky stuff with free literals here, we do have to be careful. It could easily break things if we do it. So again, there's lots of practical issues like that, but in general, this is, it's not too bad anymore. So if we want, we can look at time it. I think it's not a bad idea. So there's some easy little tricks we can do here. So we can actually pass a lambda, and I think we can just capture the formula, and okay, this one is not. This I'm just going to make consistent right now. And then we can just do the assertion here. Need to make them sets, or of course this won't compare correctly. Lists compare in order. Sets are sets, so there's no real order there, and so that would... wow. Obviously forgot to put the CDCL pass. Getting ready for CDCL. Nothing yet. Uh-oh. Okay, I mean it works. Okay. And it does work even in the case where there's an unsat, this is kind of some nice generic construction code here. So now what we want to do, instead of printing pass, we're going to want to use a time it here. So you might think, well, how on earth are you going to use time it when you want to return the solution at the same time? And this is like some nice tricks we're going to use here. So the thing we want to do probably is like even up front, just import time it. We should write more functions and stuff to do this a little more cleanly, but for now, I mean, we're in construction mode. We're not too worried about all that, so I think it's like timeIt.timeIt. And so we can do a lambda here. Now, we can't return something from this. So what we could do is we could so I'm going to try to be clever here. Just one time. So, okay, and now we're going to generalize this as well. And we can do something like all results sub 0 equals x for x in results 1 colon, something like that. Let's see if we got lucky here. Wow. So we can see the PySat, which I believe is implemented in C, is, you know, executing in about 7 milliseconds. Yeah. Okay, so here, this gives you some idea. The DPLL executing in about 3 milliseconds, or rather, this is like 7.7 milliseconds, and then 3 milliseconds, and then this is actually 10 seconds. So, big difference. But we know why, because it's totally inefficient to do that the case splitting. Now we can see though that the things have gotten faster for some of them. So I don't know what the details are of the instance, but you know, this one took 26 seconds. It was really slow. But the point is it's accurate every time, and the point is we've written some better testing code now. Now we can actually, and we're looking at the results. Now we probably should have like labels and stuff associated. So, I mean, this is like, you do something like, you know, PySat this. So it looks a little nicer to have some more information. So, okay, now we could actually add these up and do more calculations on them. But again, it's a start. And we've done this in a tricky way where we're actually capturing the result here, because results is captured like this, and we're appending to it, and it's clever. I mean, all I can say is it's clever to do it this way. We do just one run because, again, the times are so great already that we don't need to run a bunch of times and average it. In fact, we'd want to run it over all the instances maybe and take an average or something else. So, okay, fine. Yeah, and it's consistent. Like, okay, you know, give or take. It's for some instances it's always faster with DP. Some it's very, very slow. I don't know if it depends on the number of solutions, or it might depend on what variable it's choosing to split on. But actually we have something working. So I mean, that's actually very good progress, I would say. So we have to go into CDCL here. It's the next step. CDCL. So CDCL is going to start the same way. We're going to first off do some of these. Again, we could call remove subsets here. Or can we? I don't know, actually. Yeah, it's an interesting question if it would make it faster. Probably we're not going to see any speed results. In fact, it looks like it made it slightly slower. So this is why I'm saying you have to kind of be careful about this. The unit stuff already handles this, so you really have to question. But where we're going to have an explosion in the number of clauses, and it's not unit type stuff, then yeah, that makes sense. But again, initially I'm guessing these are 3 sat, so initially this is, again, in some sat systems it might be worth it. Here obviously it's not, so even just take that out. I'm looking at the times and it's gotten worse. So again though, in non 3 sat systems this could actually be a useful thing, but for DPLL actually this isn't really useful or important. Tautology, I mean, even that might not be necessary. Oh no, it's necessary. I think, yeah, that one's formulaically necessary. Okay, anyways, this is a different issue. Of course, we can always do this type of stuff. We can always do this type of stuff. Now, again, I'm not happy about the recursion here either. If I was going to do something, I'd remove this recursion. But since we only recurse on variables, and Python is going to let you do up to maybe 1,000 recursions before it's going to deplete the stack space. 1,000 variable sats, probably we'd need to go to C. It would be too slow anyways. So it's like, well, do we really want to handle that with a custom stack here? Because even if we do, we won't crash, but we'll just run forever. Again, we might want to handle 100,000 variables, but that's very difficult without using probably C. And even then, it's probably very difficult. Unless you have an easy SAT system, unlikely. Unlikely. Because if you could solve SAT systems with 500,000 clauses and 100,000 variables, that would be like next level type stuff. So, okay, CDCL. Yeah, this is gonna get complicated, is all I'm gonna say. So where is CDCL? Conflict. Oh, did I say constraint? Conflict. Driven clause learning. Okay. Wikipedia link in. So unit prop, Boolean constraint propagation, which is unit propagation. It's iteration of unit propagation, which we don't really iteratively do as maybe effectively or efficiently as we could. I could fix that very easily, but I've just decided not to do it quite yet. Basically, you could just maintain like a list of new unit clauses while some unit clauses are being resolved. Certainly would speed things along. That would be a good change. Yeah, I feel like the first step is just laying out most of the algorithmic understanding before going too deep into optimizations. But I want to make it optimized enough that it'll solve these simple 3-sat equations with 20 variables and 100 clauses or whatever it is. Maybe there's more. I don't remember how many it is, but they're decently complicated 3-sat problems. Actually, they're still, I would still say basic, but still, I want to be able to solve something that the naive search could, I guess it could solve those as well. Yeah. Okay. I guess nothing to write home about there. That is not very. Yeah, I guess the naive search would start to croak out at about 50 variables, because 2 to the 50th, obviously you're not solving that in Python, probably. It's just unlikely. Uh, Even 2 to the 32, it starts to, I mean, 4 billion operations, it's already, naive is starting to break down. So, but again, 20 at least allows you to test things quite nicely. Resolution, we have all these things. I almost maybe think I need to take a break and do some more research on this, because this is complicated. Basically, you're building an implication graph when you're doing the DPLL, but now we have to save a bunch of state information. Namely, we need to save the not only the assignments, but we need to know all of the. If we look at this algorithm here, we see that this is actually the main part of the algorithm, right? So this is just sat or unsat. Again, that'll be the same, actually. So a bunch of this code effectively will be the same. And so we'll probably make a CDCL R. We'll probably start off doing it recursively, like we've started this one off doing that. And this is kind of a dubious decision to save these free literals. I feel there's better options, but anyways, nothing's really happening. This is just kind of careful construction code, but most of the work is done right here. So that's the problem, is that when these unit propagations happen, that's implications. It's like the last variable that's at the end of solved vars -1 implies all of these different things that just happened in here. So this maximal unit propagation, which again, we don't need this loop out here. We should probably just streamline it so we only have to loop through all the clauses once, and then we can just find more unit props from the previous unit props by looking here when it goes down to 1. I mean, that actually is pretty straightforward. Maybe we should just do that right now. Here, with the pure literals, well, it doesn't hurt anything, though, to do it. So, I mean, yeah. I mean, I would just like say yeah. It doesn't even matter the order here. It's just nothing matters here. Anytime. Oh. Probably that is fine so far. But here's the problem: is now what we have to do is we have to like check for these new clauses, and if their length is 1, probably got faster. It's probably slightly faster now. So it looks like that works. So that was all. That's it. Now, in fact, actually, now we don't need this loop, do we? Technically, we need that one because we're doing these pure literals. Although we could integrate pure literals into the other one. So I mean, there's always options for this type of stuff. So the claim is we don't need to do this anymore. Yeah. Definitely don't. That's, yeah, probably a decent speed up actually. 3650, let's see, compared to last time 375. It's okay, maybe not a decent speed up. It's pretty small. But it doesn't have to go through the clauses an extra time. Yeah, I guess there aren't that many clauses in the DPLL case, so it isn't as big a deal as it seems. We're just micro optimizing. Yeah, it's almost as I said, I didn't want to do it yet, but why not do a little bit of it? Okay, whatever. So these are going to be the implications, but the problem is we're going to need, basically we need a bunch more information. This unit prop needs to tell you which clauses I believe were satisfied. Because the problem is when a conflict occurs, and a conflict occurs when you get X and not X, then the way we can resolve such a conflict is by, well, we can add a new clause, first of all, that would prevent that conflict. But to know how to do that, we have to know the clauses that led to X and not X being true. So we need clauses. We can't just take these solution variables or something like this. And when we have a conflict, we need to know a little more. So conflict, of course, would be the unsat dead end here. So when we hit this dead end, we need to kind of say, okay, did we learn anything that we can use? Can we add a clause that will help us? And then the next question is, can we backtrack all the way to the place where that new clause we learned would have prevented us from getting? So like, did we need to go so many, which is one reason why actually I think we won't be able to use recursion. That's why I want to think about this problem a little bit. This is going to be the hardest one to implement because we have to do the backtracking. And I think that already makes me feel like we should not do a recursive algorithm, but we should use a stack. So the first instinct is to just say, okay, stack equals, you know, and then the basic construction here, and then we can just say CM solve equals stack.pop. So now we have like a starting point, and maybe we can just pop stuff off the stack. It's an interesting question. It looks like that's what we would do. So we would start going off. Again, actually, you're not really backtracking entirely because you're backtracking, but you're actually still going back through the stack. You're just learning a clause while you're doing it. So we're going to have to like build some set of implications and just keep backtracking while we know that there's something that led to a conflict. So there should be a point where we stop backtracking, we stop popping off the stack and say, hey, this new clause resolves everything, so we wouldn't have gone down this branch of the tree ever, and we'll be back somewhere else. And so this is, and then we go forward from there and on different variables and hopefully get some different new clauses and such. Now, there's all sorts of problems with this approach, like too many clauses learned is a great one, and then how do you deal with that? But that's really the starting place, is to just assume that we're going to do something like this. The problem is we're going to need more than just solved variables, as I'm pointing out. We need to know the solved variables as well as the clauses, I believe. Although we have the map. That's why I'm kind of wondering, do we really need that or not? Problem is we modify the map. Because otherwise this is going to be very similar to this code. They are going to be totally similar here. You're going to do this. We're going to check for, a solution. Again, this any length 0, we could also detect, and we could somehow have this unit prop return, so we don't have to do this extra clause enumeration. But again, only in DP right now is clause enumeration causing slowness. The slowest part of this algorithm is probably right now the branching, actually. Although it's pretty fast. I mean, again, eventually it'll come down to the unit prop that'll be the slowest if we have big enough SAT systems, but the branching is also pretty much the slow part because it has to do lots of, 2 to the n maximum, and that can be very slow. So the SAT case, this case is fine. We don't do anything. We just move on with life here. Do we need to ban the solution? We have to think about that, actually. That's another... do we need to kind of ban solutions on the fly here? The assumption is going to be this is a enumerator, so it's going to just keep enumerating solutions. Could take forever on some systems, but it doesn't matter. I mean, we're just going to stick with that idea. I'll call that CS M. Yeah, this maybe because we need to make a copy at some point, and we might want to leave it on the stack. It's a question if we want to take this off the stack or not. As far as I can see, we don't want to take it off the stack until we get to unsat and we learn a clause. Or, learn and backtrack. We do the backtracking, or it's non-chronological backtracking. Really, it still is chronological because we're just jumping back somewhere. It's just, yeah, I don't know. I kind of, obviously, though, the search continues by jumping back in history, not just going back one layer, but nonetheless. The code is all going to be here, basically, besides having adapted this to a stack. Maybe it's worth adapting it to a stack just for the purpose I'm saying, namely that if we have it as a stack, it's much easier to adapt to CDCL because the main thing is going to be storing which clauses, which we might just be able to get out from the stack anyways, from the previous iteration and the map. We may already have enough information. So maybe we just need to know, instead of solved vars being a list, it might need to be a list of lists. So at each part of your stack history, which new variables were learned. And it should be enough to go and find their clauses. And when a conflict occurs, we should be able to start using the case splitting rule to learn the new clause. So that the case splitting rule should help with learning the new clause. That's basically the idea. You can look at the slides on the internet to see some of this in action. So maybe we'll make a visualization framework of this too. I think it's really helpful to see this visually, especially for small instances. There's also, other minimization techniques. on clauses that can be done. When you're learning a new clause, maybe there's a way to simplify it. Also, there's that subset, superset type of stuff. So we have to think about that as well. You obviously don't want to learn a clause that's a superset, because that's useless. Although I don't think that will happen, but again, I'm not exactly sure. But you may learn a clause that is a subset, I think. That conceivably that can happen, and that's very useful. That is the most useful type of clause probably you could learn, because that's actually saying that the original formula can be simplified, and you've found a true simplification that permanently will simplify the original formula. So, okay, I'm gonna think about this, and I'm gonna go ahead, and the next video, we're gonna actually solve this. So this is the last staging for solving CDCL. Next time, we solve CDCL, period. It's gonna happen. Right now, because today, again, I wanted to clean up DP. We have DP, DPLL, we have some timing. We did several very good things today, and so, yeah, next time we move on, we do CDCL and we make it so it truly works and it does everything in a reasonable. It should be much faster even than DPLL. We should be able to test bigger instances. We'll download more satlib with bigger instances and see that it, provably is actually better than DPLL. We won't even test DP anymore, or the trivial naive SAT algorithms. We'll forget about those, but we'll look at DPLL, CDCL, and the professional SAT libs, and we'll start doing more timing operations just to see what's going on out there. So, okay, so until next time, that was it for today.